Hello everyone, welcome to the next lecture of transistor amplifiers. We are covering the topics related to MOSFETs, how we can use MOSFETs to develop linear amplifiers. So let me give you a couple of minutes recap of what we have been talking about. For example, here is an NMOS, which is being operated in the saturation region, right? So we discussed that in order to operate the MOSFET as an amplifier, we need to operate that in the saturation and or the active region. It's a transconductance amplifier, so the output drain current can be controlled by the input gate to source voltage. So to develop a voltage amplifier, we pass this current through this load resistor and then take an output across that drain to source to have a common ground in between the input and the output. Again, this VGS is the DC bias voltage that we apply to select a quiescent or a bias point on this voltage transfer characteristics shown over here. So this VGS will produce a DC drain to source voltage and the DC drain current. So when we apply this time varying gate to source voltage, input voltage, we will get a time varying drain to source voltage, output voltage, and a time varying drain current as well. So we are going to discuss all of these expressions in more detail today. On the right side, we had a voltage transfer characteristics. Again, this is our output, this is our input. So the very first step is we select a bias point, right? So we discussed that this was a cutoff region. This was our in between points A and B is our saturation and or active region, and either of these terms can be used. And beyond this B and C points, in between B and C points, we have our triode region, right? So we want to operate the transistor as an amplifier only in this line segment A and B in this region. So the very first step is to select a quiescent point. So we select a quiescent point or a kill point or a bias point at which we bias the transistor by applying a specific gate to source voltage. Beyond that, our second important parameter in order to obtain a linear amplification is we want to make sure that our swings of the voltages should be as small as possible to obtain a linear voltage gain of an amplifier, to obtain a linear operation for the MOSFET as an amplifier. The third important component was the signal swing that is allowed. In order to determine that, we can see that over here, this is a time varying input voltage. If my time varying input voltage, the negative swing of that will go into falls below the threshold voltage, then the transistor will cut off. And the positive peaks of that will be clipped, right? So the positive output voltages will be clipped if my input gate to source voltage, its negative values will become less than the threshold value, because it's the enhancement mode NMOS, and the transistor will be cut off. Now the other important thing is the positive swing that will be allowed. For a positive swing, we want to make sure that when we allow the positive swing that will appear at the input terminal, what it will do with the negative swing at the output terminal or at the output of our amplifier. We want to make sure that this swing is also limited. The positive swing of the input VGS is also limited so that our output negative or the negative peaks of our output voltages should not be heavily distorted by the high nonlinear operation of the triode region. So we want to make sure that our transistor will neither cut off, our transistor will neither enter into the triode region for the operation of this transistor. And our quiescent point should be selected such that we will obtain a linear amplification. We will get a highest gain, and our transistor will not go into the cutoff or the triode region. In the last lecture, we also determined this small signal voltage gain. We are gonna delve more deeper into that topic today. But very quickly, again, from this voltage transfer characteristics, you can see that this is output VDS. VDS is the input. So delta VDS to delta VGS, right, can give you a slope, and that slope is equal to the gain of the voltage. Okay, so our voltage gain AV is equal to the slope of our voltage transfer characteristics. So this is the output voltage, the equation that we derived. So if we will put down the values, we ended up finding out the value of the voltage gain, which is equals to minus Kn overdrive voltage and the load resistance. So it depends on the value of the load resistance, the value of the overdrive voltage, and the and the MOSFET transconductance parameter. Okay, so let's start from here, and we are gonna talk more about the small signal operation today for linear amplification in more detail. Again, consider this amplifier circuit. We were just talking about this, right? Again, this is the bias voltages. This is the time varying voltage. So our instantaneous gate to source voltage will be the summation of the bias voltage plus time varying gate to source voltage. Similarly, our instantaneous drain to source voltage will be summation of the bias voltage plus time varying VDS. And similarly, our ID will be equal summation of the bias DC current plus time varying drain current. Right, so consider the amplifier shown over here, which is being operated in the saturation region. So we will bias the transistor by applying a DC VGS. Our time varying VGS will be superimposed on the VDS, right? So if we will take the output voltage at the drain, this will be called as this VDS, and this is going to be the instantaneous value. For only the bias voltages, again, we will assume that the time varying component is 0. If the time varying component is 0 for the bias voltages, right, our output voltages varying voltage will be 0, and this drain current will also be 0, right? Again, this is a time varying drain current, time varying output voltage, time varying input voltage. They are all 0 because we are just considering the bias voltage over here, ID. So to operate that MOS in the active region, we know that the drain current is equal to half gain VOV whole square, right? This is a saturation current equation that we discussed in the last chapter. And again, this saturation current equation or the drain current is assumes that no channel and modulation effect is considered, or the lambda equals 0. So this is the value of the drain current when we apply a DC VGS. When the time varying VGS 0, our drain current ID, this value of the ID will be equals to half gain VOV whole square. Similarly, let's find the value of the VDS. The DC value of the VDS will be VDD minus IDRD, right? So VDS equals VDD minus IDRD. Again, this is the DC value of the drain current that is flowing at the bias voltages, DC value of the output voltage, VDS. Right, so another important consideration over here is that if we want to make sure that our transistor will continue to operate in the saturation region, the condition for the saturation region was that our drain to source voltage should be greater than the overdrive voltage. Right, our drain to source voltage should be greater than the overdrive voltage. So if we want to make sure that our drain to source voltage should be greater than the overdrive voltage, so how much it needs to be greater than the overdrive voltage, right? So our output voltage or the drain to source voltage should be sufficiently greater than the output voltage that should allow the required negative signal swing. So what does that mean? We can go back to quickly to the voltage transfer characteristics back here again, right? So that statement means that our output voltage, this VDS, right, or this capital VDS for the bias value, this bias value should be sufficiently larger. Here's the overdrive voltage. This is the edge of the saturation where VDS equals to overdrive voltage, right? So we want to make sure that in order to allow this negative swing to occur and not truncate and not distort that negative swing, our DC value of the output voltage should be sufficiently greater than the overdrive voltage. We can also operate the transistor as an amplifier in the saturation region by operating it over here, right over here, right? By operating it right over here. But will it allow the negative swing of the output voltages or not? So that's the question, right? So that is why allowing the voltage swing that is allowed at the input that will not make the transistor to either cut off or enter into the triode region is very critically important. And this is the whole discussion of selecting the quiescent point is. And we are having a similar discussion now that we are selecting a quiescent point, this output voltage value VDS, such that it is sufficiently greater than the overdrive voltage, which will allow the negative outputs of the negative peaks of the output voltage still in the saturation region and do not distort them while being in the triode region. Okay, so where are we? Okay, so we discussed that. Now, after the bias point, let's say that what will happen when we apply this time varying component, right? So initially our gate to source voltage was this capital VGS, the bias value. Now we will apply this time varying VGS as well to the input voltage. So the total instantaneous VGS will be equals to the DC VGS plus the time varying VGS component. Similarly, we now right, so over here we calculated, we find out all the DC components, right? The DC VGS, the DC ID, and the DC value of the output. Now we are going to find out what will happen when we apply the time varying component, right? So our total instantaneous value of the gate to source voltage at the input will be the summation of the two, the time varying component and the DC value of the gate to source voltage. Similarly, when we do that, our instantaneous value of the drain current will again also be the summation of the two. And so what do we get is over here, right? So essentially we know that our drain current is equals to half Kn VOV whole square. This VOV is essentially equals to this VGS minus VT whole square. And now this VGS, we know that this is equals to this capital VGS plus small VGS. So essentially, starting with this drain equation is for the saturation current. We can expand it to this thing, VGS minus VT, where this is our total drain instantaneous gate to source voltage, which can be expanded over here. So this is what we essentially ended up writing over here is. Okay, so once you get this equation, you can easily expand out this term, a minus b whole square. So we can see that this is half Kn, so we get three terms. Now look at all the three terms very closely. So the first term is half Kn VGS minus VT whole square, right? So this term shows this DC value of the gate to source voltage. So this means that this is what our DC drain current is when no time varying component was present. The second term shows a linear amplification or a linear relationship in between the drain current and the input voltage VGS. The third term shows a non-linear relationship, the square relationship in between the input voltage and the output drain current. So if I have to look closely and I would say that I want to operate my transistor as a linear amplifier, this means that as I change my input voltages, my output currents will be linearly amplified. If I want to achieve that, I want to make sure that I will minimize this. So what I'm going to do is to find a condition at which this will become true. Okay, so this is the same DC bias current that I talked about. The second term shows our direct linear proportionality here. And the third term is about the nonlinear distortion because of the VGS whole square. Okay. So how I can determine the condition in which I want to make sure that my amplifiers still have a linear operation, right? So I want to minimize this term, or I want to make sure that my second term is sufficiently larger than the third term, right? So what I do is I will say that my Kn VGS minus VT VGS should be sufficiently larger than half Kn VGS square. So Kn and this VGS, so I would get VGS minus VT should be sufficiently larger half of VGS. So this is overdrive voltage, 2 times overdrive voltage should be sufficiently larger than VGS. So that could be rewritten as VGS should be sufficiently smaller than 2 times the overdrive voltage. So this condition needs to be true to make sure that this third term can be neglected, which is a non-linear amplification, and our amplifier behaves as a linear amplifier. So this is exactly what we did. Our third term should be much smaller than the second term. And once we do that, we can reach out to this condition again in which we say that our gate to source, time varying gate to source. So what does this show or represent? Our time varying gate to source voltage values that will appear at the input should be sufficiently smaller than 2 times the overdrive voltage. If this condition will be true, our amplifier will behave as a linear amplifier, right? So this is what is called as a small signal condition, right? The VGS should be sufficiently smaller than 2 times the overdrive voltage. And when this is satisfied, the third term will be neglected, which represents the nonlinear distortion. So what will be so by now we talked about the total instantaneous gate to source voltage, the total instantaneous drain current, So let's look at the drain current in a different way, or probably kind of a similar way, different equation. So over here again, this is the total instantaneous drain current. This is the DC value of the drain current, and this is the time varying component of the drain current. And now I will assume that this condition is met. So I'm re-looking at the drain current values, or the instantaneous value of the drain current, when this condition VGS is very, very small than 2 VOV is met, or a small signal condition is met. When that is true, I will go back and I can easily neglect the third term, right? Okay, so when we do that, our time varying component, right? So what I left with in this equation, going back to this ID, is we have this component was equal to capital ID, right? And if I will neglect the third term now, the second component will become the time varying ID, right? So our instantaneous ID will be the DC value of the ID plus the time varying component ID with a smaller ID, right? So that time varying component is equal to this, right? And again, this term is very, very larger than the third nonlinear VGS squared term. That is why we are neglecting that term. Now from this term, you can we can also see that we can use this term to find out the transconductance gain of the amplifier, right? Using the ID and the VGS. So if you will do ID over VGS, you will get Kn VGS minus VT, which is equals to Kn VOV, right? And what is ID over VGS? This is GM. So our transconductance can be transconductance gain. The value of the transconductance gain, it can be written as Kn VOV over here, right? So our GM is the MOSFET transconductance parameter and the gain value. This also represents the gain value. Okay, so one thing is we will come back to this GM value again, because we will realize that this value is sufficiently, we are going to use in multiple problems and in multiple amplifier configurations. In the next lecture, we're going to do different amplifier configurations, derive out different equations, and we're going to use this transconductance parameter again. The value of the transconductance again parameter is equals to KNVOV. Okay. So here is the small signal operation graphical representation. Again, here is our output drain current. Here is our input gate to source voltage, right? And now here is a time varying input, right? So again, this is the bias value of the input voltage, right? Here is the bias value of the drain current ID. So when we have a superimposed time varying VGS on the bias input voltage, we will get the amplified version here of the output of the drain current. Please note that over here there is no inversion. As you are increasing the gate to source voltage, your drain current is increasing, right? Because you can see from this plot that it's a linear relationship, or it's a direct relationship rather than an inverse relationship. And this gain in between the changes in the ID to the changes in the VGS is equal to the slope, right? And we have seen that ID over VGS is equals to GM. So GM represents over here, the transconductance parameter represents over here the slope value as well. Right, this can also be rewritten as over here if you will take partial derivatives of this. Okay, so let's find out another equation for the voltage gain. Now we are going to kind of revisit the voltage gain again. Consider the amplifier circuit that I have shown you, this amplifier circuit over here. So our total instantaneous voltage VDS can be written as, again, it will be equal to the capital VDS minus the time varying, plus the time varying small VDS. However, if I will go back to the circuit, okay, so this is the instantaneous VDS. So this instantaneous VDS is equal to VDD minus instantaneous ID into RD, right? So this instantaneous value of the VDS is equal to VDD minus ID into RD. Okay, so this is over here. Now what we can do is, now we know that under the, again we are assuming over here the small signal condition is amplified, in which we neglected the third term by knowing that the time varying input voltage is very smaller than the 2 times the overdrive voltage. When we meet that small signal condition, our drain current is proportional to this, in which it is proportional to the summation of the DC bias current and the time varying current. Right. However, so the only difference is that our time varying current, the only difference, so this term remains the same, irrespective of whether we are ignoring the third term or not. This term will change, right? Because this ID is either, yeah. So this ID is either composed of both of this second term and third term, right? Both of these terms, or either it will be this only second term. Now, since we are assuming a small signal operation to be true, so we can ignore the third term, and our smaller ID is only equal to Kn VOV VGS. Okay, right? So what we did is we ended up putting this ID value over here, and this is what we get: VDD minus RD, ID plus ID. Right, so I can easily open up these brackets, and we can find that this is proportional to, right? So if you will open up these brackets, you will get VDD minus RDID minus RDID. Now, this VDD minus RDID is the DC value of the gate drain to source voltage. So that is why our total instantaneous drain to source voltage is a DC drain to source voltage minus this component, RDID. Right, so VDS is a DC component of the drain to source voltage, right? And this is our time varying component. So I can also write this time varying component as VDS. Okay, so I can all right, so our VDS now equals to minus IDRD, right? And I know that my drain current is equals to GM into VGS. Where did I find this out? Over here in this equation that we ended up finding. So our GM is equals to ID over VGS, or our ID is equals to GM into VGS. So using that equation, I can put that equation over here in ID over here, right? So after putting these values of the GM VGS here, our drain to source voltage will come out to be minus GM VGS into RD. Now from this equation, I can easily find out the voltage gain for the small signal operation. So our VDS, output voltage, to the gate to source voltage, again these are the time varying input signal components, is equals to minus GM into RD. Again, this is another value of the voltage gain for the small signal operation. Okay, so also remember this voltage gain value as well. Again, the minus sign over here also indicates that the output voltage VDS is inverted, right? Because the voltage transfer characteristics that were seen earlier. Now let's revisit all of these concepts very quickly in a more graphical way. So let's look it over here. Here is our input voltage VDS instantaneous. Here is our output voltage instantaneous drain to source voltage. This is the DC bias value VGS, right? And this is the VDS, the DC bias drain to source, the DC output drain to source voltage when no time varying component was present. So the first thing to note over here is the output voltage is inverted, or 180-degree out of phase, right? So as input is decreasing, our input is increasing. As it is increasing, it is being decreasing, right? So the first point is it is inverted and amplified. Okay. Now let's look at the second component, the amount of the amplification. We know that the amount of the amplification is proportional to the GMRD from here, right? Minus GMRD. So our output is amplified by the amount of GMRD. And over here, the negative sign over here is missing, which essentially just indicates that our signal is amplified, right? However, this peak to peak amplification is proportional to GMRD. Okay, so this is this equation. All right, the third important component is over here to obtain a linear amplification, our voltage swing of the input voltage, right? So this is the voltage swing of the input voltage. Our voltage swing of the input voltage is very smaller than 2 times the overdrive voltage. So our small signal operation is true. The fourth important component is our smallest value of the output voltage, the VDS, once the swing is applied. The smallest value that is allowed at the output should be greater than the overdrive voltage. No, sorry, this is not the overdrive voltage. So the minimum value of the drain to source voltage, or the smallest value of the drain to source voltage, which is output voltage, should be greater than the overdrive voltage to obtain a linear amplification. Otherwise, the transistor will enter into the triode region and the negative peaks of the output VDS will be heavily distorted, right? So this thing is the overdrive voltage. Then we have a fifth component. Our fifth point is that the maximum value of the output voltage should be less than the supply voltage, VDD. And why is that? This will ensure that the transistor will not cut off. Okay, so these are kind of a summary slide representing in a very graphical way, representing all the important concepts that we talked about. Okay, now we are going to move towards developing some equivalent circuit models, and that is kind of an important topic because we are going to use these equivalent circuit models and the input these circuit model representations in our next lecture, where we're going to talk about different amplifier configurations. Okay, so here's a small circuit equivalent model. You have seen this circuit before in the last lecture, in the last chapter as well, when we are talking about a MOSFET, finite output resistance, and channel length modulation effect. This is an NMOS. Here's a gate terminal, source terminal, a drain terminal, right? This is a time varying input voltage, right? And it's a transconductance amplifier again, which is in which a constant current can be controlled by a voltage source, right? So voltage source is controlling the current, output drain current. Okay, and we know that where this value is coming from, we know that ID equals to GMVGS. We ended up driving it multiple times here. Right, okay, you can also look it over here. ID is equals to GM into VGS. Okay. So this is what we have, and let's talk about it. So the first one is our FET. MOSFET behaves as a voltage controlled current source, right? So this is our input, this is our output, and this is the value of this output constant current value related to the MOSFET transconductance parameter. Another important point is that input voltage to the transistor is very, very high, ideally infinite. Another important concept that we discussed earlier is that the output resistance of the NMOS is also infinite, considering when we operate the transistor in the saturation region, once the channel is pinched off, this is again our values of our drain current, and this was our drain to source voltage. So as we enter into the saturation region, our current was constant, right? Slope 0 and resistance infinite. So our output resistance was infinite, and it was not it was infinite. So this was when we assumed that there was no channel length modulation effect. Then we studied the channel length modulation. Then when the VDS becomes equals to the overdrive voltage, the channel is pinched off. But as the VDS is further increased, the channel length starts to reduce and the drain current starts to increase. And when the drain current starts to increase, we got a finite resistance, or a finite slope and a finite output resistance, which this represents over here. Okay, right? So with the channel length modulation effect, there was a finite output resistance R0, which is represented over here. And we also find out this value of the R0 while studying the channel length modulation in detail, which is dependent on directly proportional to the early voltage, VA, early voltage, and inversely proportional to the drain current. This drain current is assuming lambda equals to 0. Okay, so important thing over here that if we replace the MOSFET with the, so we earlier we derived the gain expression of the MOSFET, right? But that gain expression was when we considered the output resistance to be infinite. However, if we consider a finite output resistance model with channel length modulation effect in place, then our gain parameter will be changed. Then that output resistance, finite output resistance, will appear in parallel to RD. And our voltage gain, this VDS over VGS, will be changed by this factor. Now our RD is in parallel with R0. And this means that our overall voltage gain will reduce. So this will result in the reduction in the magnitude of the voltage gain. Also, please note that we did all of this analysis for the NMOS. PMOS analysis is essentially the same. We just use the modulus values. So let's quickly look at the transconductance parameter again, this GM parameter. So we know that GM is equal to ID VDS. We just discussed that today, right? So GM is equals to K and VOV over here. You can also further expand this equation, Kn by Kn dash W over L and VOV by VDS minus VT, Kn dash W over L, VDS minus VT, or yeah, just kind of expansion of these terms and writing the same expression in different ways. So importantly, what we want to do over here, we want to see that on which factors does this GM factor depends on. In terms of the, especially looking at the drain current or the DC value of the drain current. So what we do is using these equations, we know that, so this is our drain current during the saturation. Yeah, so this is the drain current in the saturation region. So what we want to do is we want to replace this value of the VOV into this equation, right? So or you can replace this value of the VOV into this equation. So initially our GM equals K and VOV. Now coming over here, our 2 times ID over Kn equals to VOV whole square. So this will be this. Let me replace this over here. So GM is equals to square root 2 square root ID over square root Kn into square root Kn. Oh, sorry. So this square root will ended up putting a square root on the top over here, or 1/2. So our GM now will depend on the square root 2, this term, right? So we know that this Kn is proportional to Kn dash into W over L. So 2 Kn dash W over L square root into ID. So our transconductance process parameter under two conditions, under the condition of the linear amplification and under the condition of the finite resistance, is proportional to the square root of the aspect ratio and the square root of the drain current. So these are the two conclusions that we can draw from this analysis. Okay, so there is one more equivalent circuit models, the T equivalent circuit models that we are going to discuss today. And these equivalent circuit models are very, very important because they will be used for different, while the design of the different configuration amplifiers, which we will discuss in the next lecture. So let's look at the current models in different ways and how we can kind of rechange it or reconfigure them. Okay, so let's start with A. We have again a gate terminal, a source terminal, a drain terminal. We already discussed that. This is the value of the drain current that is flowing over here, this value. Our gate current is 0 and our source current. The direction of the current is from, just go back to the NMOS, how the channel is induced and where the charge carriers are flowing, and how the current is constituted. So you can easily find out all the directions of the current. In case of an NMOS, the current flows from the drain to the source. Okay. And this is our time varying input voltage here. Right. So the very first thing that we do is as we move from this A to B, so once we move from here to here, if I want to keep the terminal characteristics the same, there are some modifications that I can do to this equivalent circuit represented in A over here, right? So the first thing that I can do is I can add another current source here, right? It's essentially, rather than adding a current source, I'm just representing the same current source in this branch as well, right? Because this is the same current that is flowing in this entire branch. If this is true, then I can also show the same current source over here. This is the current ID, which is equals to GMVGS add node X. So I defined this node X and added this current source here, which is the same current source because we have a same drain current that is flowing from drain to the source. Now again, keeping the terminal characteristics the same, what I ended up doing is I ended up connecting these two together, right? And this can be done without changing any properties of the terminal. Again, our gate current will be 0, that is going over here, source current is here, drain current is here, which is essentially the same. I connected the gate terminal to the node X. So this was the representation of the C, and now we can move to D. This is the representation of the D. So what we did in the D now is, you can see that I can move this branch up here like this. So this is the first thing that I did. I moved the drain terminal over here on the top, in which the drain current is flowing and the current is the same, GMVGS. My gate terminal is exactly the same with the gate current to be 0, IG equals to 0, going to the node X. And then I have, look here closely over here, I have a in between gate and the source terminal, I have a gate to source voltage appears, that is plus minus VGS, right? And then in this branch, I have a current GMVGS that is flowing, right? So if I have to find out the resistance in between the gate and the source, right? If I have to find out the resistance in between gate and the source, right? So I know that V equals to IR, R equals to V over I, right? So I can see that it will be VGS over this current, which is equals to GMVGS. So I can divide these two, and the resistance value in between the gate and the source will be equal to 1 over GM. So this resistance appears in between the gate and the source, while this voltage drop appears across this resistance, and the source current is this. So this is another representation of the equivalent circuits. So what we will do is, what is the usage of drawing this different equivalent circuit models? We will see its application in the next lecture, when we are going to develop different amplifier configurations, and we will see that how we can use this different representations of the MOS-FET equivalent circuits. Okay, great. So with that, we will wrap up our lecture today, and in the next lecture we are going to talk about different configurations of the MOS-FET, and which includes the common source amplifier, common gate amplifier, and the common drain amplifier. So we're going to discuss the more details and how to find out different gains values of the voltage gain values of those different amplifier configurations for the MOS-FET. All right, with that, thank you so much, and I will see you in the next lecture. Bye bye.